Assalamu alaikum. This is lecture 9 on digital control system. We are discussing chapter 3, that plane analysis of discrete time control system. The actual design analysis and the design that will be covered in chapter 4. The prerequisite of that is been discussed in this chapter. So we already have one class on this chapter. So today we'll be covering article 3.3, obtaining the Z transform by the convolutional integral. Okay, so let's begin, inshallah. Article 3.3. So Z transform using convolutional integral. Okay, so assume a simple diagram of an impulse sampler with an arrow, of course, denoted by del t. Xt is the continuous time signal, and the corresponding sample signal is star t. And we have seen previously that x star t is basically summation of k equal to 0 to infinity xt, which is the signal strength. In the previously, actually, t has been replaced by kt. Same here. If you want, you can do that. Del t minus kt. So kt delayed version of your impulse, unit impulse signal. So now that is your, you can actually see, since it is just signal strength, we can actually isolate the train of pulses k equal to 0 to infinity del t minus kt. So eventually, since the magnitude at any particular instant t equal to kt is given by a magnitude 1, so multiplying by 1 is actually eventually the magnitude of xt at that particular instant. So we already know that Laplace transformation of your del t minus kt is basically a delay by kt. So it will be simply, the magnitude is 1, so it will be simply e to the power minus kts. Okay, so since we have a summation, so let's see how the summation behaves in the Laplace transformation. Equal to 0 to infinity, so it will be just a series, nothing else. Del t minus kt equal to then 1. The first one is delayed by kt, so e to the minus kts. Second one is 2 kt, so basically second one will be sorry, the k is basically from ranging from 0 to 1. So since we're writing the series, it is better to write in terms of numbers. So first one will be delayed by 1t, so ts, then to the power minus 2ts, to the power minus 3ts, and goes on infinitely. So since this is your a, the first value, and this is a common ratio r, so we know that our a by 1 minus r is our so the result of your infinite series. Definitely if it is convergent, so region of convergence is also an important aspect, but in our case we generally assume that it is always having, as long as it is having a range, we are happy with that. So from the control system perspective, so this is what I know is our Laplace transformation of the series. Now, since your x star t, or Laplace transformation of x star t is your x capital X star s is the Laplace transformation of your x star t, and AT is the Laplace transformation of two time domain signal, basically x t, and it's k equal to 0 to infinity del t minus kt. So basically two time domain signal. One is this one and one is this one. So from the theory of the Laplace transformation, we know that if this is the scenario, the Laplace transformation of two time domains signal is not simply their product in the Laplace domain. So basically, we cannot say that it is equivalent to xs and then whatever we have figured out into 1 by 1 minus e to the power ts. So we cannot say that this is not true according to the Laplace transformation theorem because they're multiplied. So we have to have that convolution integral to figure out the result of this multiplication of the two time domain signal. So, so what was the theorem says according to the Laplace transformation theorem? We know that if we have two functions, say one is gt and one is ft. So we have two functions. And now if we have Laplace transformation of multiplication of these two, ft and gt, then it should give us a formula like this, 0 to infinity, integral over 0 to infinity, ft gt e to the minus st dt. And that will give us a solution, which is eventually known as convolutional integral, is 1 by twice pi j integration over c minus j infinity to c plus j infinity. Actually, integration over a line ranging from minus infinity to 2 plus infinity with some shift from our imaginary axis. So C is basically that shift. So this line is actually representing a line that is parallel to our imaginary axis. So Fp Gs minus P dp. So two parameter, S is one parameter which we usually know, and P is another parameter in transforming the another plane, P plane. So this is our theorem says. So before going to how to convert this into using this formula, we have to actually, it's better to see the derivation of this one. Okay, so then we'll use this formula to find out that what is the corresponding Laplace transformation of that equation that we are interested about. So derivation is also kind of straightforward, not too much complicated. So let's start with the derivation first. So Laplace transformation of ft gt is equal to, just by formula of the Laplace transformation, ft, just put all the values, e to the minus st dt. So formula. Now, inverse Laplace transformation or inversion integral says that ft from the inverse Laplace transformation. Okay, so or sometimes it is also known as inversion integral. So what we know is ft is 1 by twice pi j. C minus j infinity to c plus j infinity fs e to the power st ds. We always assume that t is greater than 0. And what is c? C is the abscissa of convergence, or basically line of convergence. So if we now put this value of ft into this equation, then what we get is Okay, so 1 by twice pi j 0 to infinity, then c minus j infinity to c plus j infinity. Then you have fp. We are introducing another parameter because already in this equation we have s. So e to the power pt. Then you have bp with respect to p. So then you have gt, the previous one, e to the power minus st dt. Okay, so since we are assuming a uniform convergence, so whether the integral is the line integral is done first or the integral of 0 to infinity is done first, it may give the same result. So that is why the integral sign can be changed. So considering that uniform integration or uniform convergence, we can just alter the order of this integration. So in that case, we can write in this way, the integration of c minus j infinity, c plus j infinity, fp, pp, and 0 to infinity, gt, e to the minus s minus p t dt. Okay, so now if we note that this portion is nothing but, second portion is nothing but a Laplace transformation formula. Only the thing is that in the Laplace transformation formula, you have e to the minus st. Now, instead of that, what you have is e to the minus s minus pt. So, Laplace transformation of if it was e to the st, it would have been g of s. Now, since we have e to the power minus sp, s minus p, so it will be simply gs minus p. So, and this is also inverse Laplace transformation of f p. So it will give us also corresponding Laplace, inverse Laplace transformation. So we can just keep it as it is, and hence what we are going to get is 1 by twice pi j integration minus c minus j infinity to c plus j infinity fp dp. And this one is just simply g s minus p. And now this dp actually can be moved here. So now we have a simple inverse Laplace transformation. Actually, this is what is basically known as convolutional integral. Okay, so this is the formula that we're supposed to derive, and now using this formula, whatever the function that we had, two functions, one is xt and another one is summation of k equal to 0 to infinity xt. So this is our one function. This is our one function, and we can assume that this is our ft, and we can assume that this is our gt. Okay, so now based on this assumption, what we can write is x star s equal to Laplace Laplace transformation of xt summation of k equal to 0 to infinity del t minus kt. Okay, so as you just said that we are going to assume this one as a ft and this one as gt. So we can write as using just simply this formula 1 by twice pi j. This is integration over c minus j infinity to c plus j infinity xp And then we already figure out what is the Laplace transformation of this second one. And we know that this is 1 by 1 minus e to the power ts. Now s is simply will be replaced by s minus p. So we can write 1 by 1 minus e to the power minus t s minus p. And then finally dp, the integration operator. So this particular equation is basically known as in the convolution integral. Okay, so using this convolution integral, we have to find out the z transformation. So this is a bit complicated to calculate the actual response of our actual z transformations in this formula. So that is why we'll take help of the control integral, basically the residue we are interested to take help of. So that is why, even though this c minus j infinity to c plus j infinity, that actually means that we have a line something like this. So this is c minus j infinity, and this is your c plus j infinity. So to take help of the control integral or to take help of your residue theorem, what you can do is, this is the direction, then we can take a infinite half semicircle, either in the left half plane, infinite semicircle, or which is counterclockwise, or a infinite semicircle in the right half plane. So right half plane. So basically, this is clockwise. Okay, so this anticlockwise and clockwise is also have some effect, because the integration over anticlockwise is positive and the integration over clockwise is negative. So the sign has to be taken care of in that case. So basically, what we can take is, if we can form this contour closed loop using this one. Okay, so in this closed loop, how many poles we have? We can have the residue of that one. That will be your simply the integration of that one. And also, if we know this integration only about this semicircle, either in the left half plane or in the right half plane. So if you know the magnitude of that one, so from the total integration of the contour, if we just subtract that one, that should give us the integration. So the condition provided that the integration over the infinite semicircle, whether left or right, has to be a constant, so that we can easily subtract that one. So what we are interested about is we want to calculate our excess in this way. Excess equal to 1 by twice pi j integration. The closed contour, we are not giving any direction here, clockwise or anti-clockwise, because it will depend on whether you're taking the right half plane or the left half plane. The right half plane, it will be clockwise, and in the left half plane, it will be anti-clockwise. So bottom line is integration over a closed path of the same function, that is xp by 1 minus e to the power minus ts minus p dp. And from that one, the added one, the semicircle that we have added in the clockwise or anti-clockwise, that one represented by capital gamma, so has to be subtracted. So if you get to give 1 by twice pi j, so include that, and then you have xp by 1 minus e to the power minus ts minus p. Okay, so we calculate the integration over this contour, either left half plane or in the right half plane, and then from that one we just subtract this one or this one. Okay, so based on which one you are actually taking. So this is the way of calculating the z transformation, because x star t, x star s, if you know, you can simply replace the s by 1 by t ln z to make it a z transformation. Okay, so let us go for the two separate cases. One is using the left half plane and the other one is using the right half plane. So, but before that, just assume that if you have any, just recall, if you have a transfer function xs, and it is represented by two polynomial numerator polynomial qs and the denominator polynomial ps. And then if you want to find out if they are strictly proper, that is the order of the denominator is higher than the order of the denominator. In that case, if the limit s tends to 0, x of s, if you want to figure out, then you're going to find that since the order of the denominator is higher order, so it will have more s in the denominator than the numerator, whatever it has. So 1 by infinity is becoming 0. So that is why we can say that if the equation is strictly proper is this condition where the numerator is having higher values than the denominator. In that case, we don't have to bother about the x's because it will always give 0 if you take the infinite semicircle. So that will actually help us to simplify our calculation. So let's start with the first one, that is case 1, that is using left half semicircle. So this is for math problems. Mainly, this left half plane will be used to simplify the mathematical problems. Okay. The other one will be used to actually understand. The other one is a bit complicated. The right semicircle, using the right semicircle. So that one is complicated. So we'll not use that for the solving the math problems. Rather, that will be used for explaining some of the theorems in the later part of this chapter and in the chapter 4 as well. But that is also essential. So now what we actually want to do is we want to draw a semicircle. We have to draw the diagram first, then we'll try to explain. Okay, so this is these are the poles of arbitrarily, of course, the poles of your poles of XP. Okay, and the poles of 1 by 1 minus e to the power t s minus p is this. Okay, so these are actually poles of 1 by 1 minus e to the power minus t s minus p. So in the first method, we're drawing an infinite semicircle. So this line of abscissa, a line of convergence or abscissa of convergence, which is starting from minus c minus infinity to c plus j infinity, that is actually somehow you have to choose the line in such a way that it actually separates those two poles. Okay, so the pole of 1 by 1 minus e to the minus ts and the poles of xp, they have to be separated by this one. I have one question in mind. If it is not separable, then what will happen? So maybe in the later we'll try to answer this one based on some references. So far, I haven't encountered any problem that is having this kind of scenario. So this is your semicircle and the contour. Okay, so using this one, what our formula is becoming is x star s equal to 1 by twice pi j xp by 1 minus e to the minus ts minus p. So in the it has to be counterclockwise. Minus, now the contour, we have to subtract the value of the infinite semicircle. So it is a line integral, so it is not a contour. So gamma L. So left half semicircle with xp and 1 minus e to the minus t s minus p dp. So this portion is vanishes. Why vanishes? Because we consider that xs is basically strictly proper. So now your q of s divided by p of s, what do we have? If the integration is, since it is in the infinite semicircle, so the value of s will be always infinity, and because of that, this one will be vanishing to 0. So this is 0 now. Whatever we left with is we have to figure out this control integral to find out the x's. Now, whether you recall or not, this whole thing is your function. So we using the residue formula, what we have seen is that the residue formula says the summation of all the residues of the function at poles of the enclosed pole. So in this case, which poles are enclosed? XP. So the poles of XP. Because if the poles are outside the contour, the integral is always 0. So it doesn't make any difference whether we take them or not. So that is why we always write in this way as a result. So summation of all the residues of function, which is our xp by whole function, we have to mention, but the poles of only xp because they are enclosed. Okay, so xp at pole of xp. Okay, so simple idea, the idea that we have developed in the last chapter. So now, since we are happy with that one, so next step is just obtaining the Z transformation. So this is actually X star S. So now if S is been replaced by 1 by T ln Z, or Z is been replaced by e to the power TS in this equation, in that case, we can easily figure out the Z transformation. So eventually the Z transformation XZ is summation of the residues of XP. Now your equation here, 1 minus e to the power minus TS e to the TP, or at pole of XP. So I'm not writing the whole thing again and again, just to simplify the idea. This is your XP, then you have 1 minus, this is basically Z inverse. So you can write 1 by Z as well. So we get about TP at all of this, okay? So finally, if you just simplify a bit, summation of residue at Z will become in the numerator as well. So XP, Z, then Z minus e to the power TP. Now, notice the fact that in the now equation is only in terms of P. So the S is now absent. So now if you want, then we can actually write same equation as before, because you can just replace the P by S to make it more familiar, whatever we know so far, because only one operator is available now. Okay, so this is what we can write. Okay, so now how to find out the calculate the residue? I think you can recall from the last chapter, and that if it is a simple pole, or the simple pole, we can write in this way: limit S tends to Sj. Then you just multiply with that simple pole with whatever we have already figured out, Z minus e to the power ds. Okay, so this is in case of the simple pole. In case of multiple pole at, say, multiple pole at S equal to Si of order Ni. Okay, so if this is the case, in that case, Ki will be factorial. Ni is the order, so one less than that. So Ni minus 1 factorial, and then limit you have to set as it tends to Si. But before that, you have to have the differentiation with respect to S, of course, ds lesser than 1, so Ni minus 1 and Ni minus 1, S minus Si, multiply the whole thing with that function that we have, Z minus e to the power ds. Okay, so these are the two things, two ways to find out whether we have a simple pole or multiple pole. Based on that, we can go for our solution. So now let us look at the one example, example 3.1. Example 3.1. What it says is that you are given with xs equal to 1 by s square s into s plus 1. What they want you to find out is find out the z transform. So xz you have to obtain using convolution integral. Convolution integral. Okay, so if they mention using the left half plane is better to go left half plane. And even if they don't mention anything, for solving the math problem, if a particular system is given, you always prefer left half plane. So unless otherwise explicitly mentioned, then go for the right half plane. You always prefer the left half plane. Okay. Okay, let's go with the solution. Now we have two poles. One is a simple pole at -1, and one is a multiple pole at 0. So a multiplicity of 2. Okay, so these are the scenarios. So we can write that xj is the residue of summation of the residue of x s is j into j minus divided by j minus e to the power ts at the poles of xs. Okay, so what we can see so far is that we have multiple pole at 0. So using that multiple pole formula, 1 by multiplicity of 2. So basically 2 minus 1 factorial. Then we have limit s tends to 0. Then we have, since it is 2, so simply d by ds. Then the pole is at s equal to 0. So you have to multiply with s square, the whole function. So basically 1 by s square s plus 1. Don't forget these parameters. Okay, so these are also present. So z minus e to the power ds. So this is the multiple pole. Now for the simple pole, just limit s tends to -1. You must multiply with that one, s plus 1. 1 by s square, s plus 1, then z by z minus e to the power ts. So second one is relatively simple and straightforward. So the first one, so limit s tends to 0. Factorial of 1 is 1, so we don't have to bother about that one. Then we have, and also we can see that s square getting cancelled out. So, and z is a constant, so you can just keep the z to the front without any trouble, because we are doing the differentiation with respect to s. So now what do you have two functions, s plus 1 and z minus e to the power ts. So you can just write in this way using just inversion so that you can do the differentiation with ease. So we inverse into z minus e to the power ts inverse. So just taking the inverse of both of them. And then we have it's equal to minus 1. So this one is cancelled already. So minus 1 whole square is equal to 1. So it will be simply z by z minus e to the power minus t. S is replaced by minus 1. So next is multiplication formula, differentiation with u and uv. So use that formula here. So limit s tends to 0. Now it will be minus 1 will be coming first, then s plus 1 minus 2. Okay, and minus s that is 1, so it will be remaining as it is. Plus we have, okay, so don't forget to put that one, z minus e over ts minus 1. And then next one will be this differentiation of that one. So plus minus 1, then we have z minus e to the power ts. Then 2 to the power minus 2 now. Then you have ts, so t will be there. Okay, and also don't forget about s plus 1. And then we have z by z minus e to the power minus t. Okay, so what you can see here is, okay, one thing I think we have missed is this one. E to the power ts will be also integrated. So e to the power ts will be also available here. Because the integration of the exponential is same as that, so it will be remaining as it. Then actually you have to integrate ts, so it will be with t. So what we have is z limit is tends to 0. Then you have another thing we have missed, because you have a negative sign here. So negative sign will also be here. So negative will be positive. So you can write this one first. So basically what we will have is e to the power ts t, then s plus 1, because it was inverse. So sometimes simple things may become a bit complicated because of not using these things very regularly. So I recommend you to practice a bit, otherwise you may be in difficulty in exam hall. I mean, online exam. So next is z minus e to the power ts, and you have s plus 1 whole square. And obviously the z by z minus e to the power minus t. Okay, so now we can also have the flexibility to actually set s equal to 0. Now, if you set s equal to 0, the equation will be very, very simplified. It is e to the power 0 is 1, so it will be replaced by 1. This one is also 1. Okay, so what we will have, and this is set equal to 0, so this one will be also 1. So we will have t by z minus 1 whole square. Similarly, this one will be 1 as well. So, and also this one vanishes because it's equal to 0. So by 1 by z minus 1 plus z minus e to the power minus t. Okay, so you can just do a bit of simplification with z minus 1 being taken common. So we will have t minus z plus 1 plus z minus e to the minus t. Okay, so you can now go to do a bit of simplification again. Z minus 1 whole square, z minus e to the minus t, and do the calculation. I'm leaving it for you. I'm just writing the, because just simple calculation, so I'm just writing the final equation. That is 1 minus z to the power minus 1. Obviously, it will be coming in z form, then you have to divide the numerator. Actually, it's better to write there. So write z minus 1. I'm just skipping one line maybe then. Okay, so z minus e to the minus t, z square, t minus 1 plus e to the power minus t plus z 1 minus e to the minus t minus t to the power minus t. So since the order here is z square and z, so z cube, so numerator and the denominator, if you divide by z cube, then it will give you the solution in terms of z inverse. So basically, t minus 1 plus e to the power minus t z inverse plus 1 minus e to the power minus t minus t to the power minus t z to the power minus 2 divided by 1 minus z inverse whole square, then 1 minus z inverse e to the minus 2. So that is your solution. Okay, so let's go for the next one, that is evaluation of the convolution integral using the right of plane. So the case 2. Case 2, right of plane. Okay, so now things are going to get a bit complicated. So let's start. Okay, so again, we are assuming the poles somewhere here. These are the poles of xp, and the poles of 1 by 1 minus e to the power minus t into s minus p. So how the poles of that one is an infinite number of poles like this. We also have to derive that. So again, this is your c minus j infinity to c plus j infinity. Then you have added infinite semicircle and the right half plane. So since starting from minus infinity to the plus infinity, this is the direction. So, and because of this direction, we have to include a minus sign in the integration. So far, what we know is that our integration of x star s is basically 1 by twice pi j c minus j infinity to c plus j infinity. P by 1 minus e to the minus t s minus p dp. So for the right hand plane, this equation can be written as integration. Okay, so using the right half plane in the clockwise direction. So a negative sign has to be introduced here, and then you have a form c minus j infinity. Actually, since it is a clockwise, so the limit you can avoid because it is a contour. So we have, and also the constant thing we forgot. So minus 1 by twice by j. Then you have xp 1 minus e to the power minus ts minus p dp. Okay, so then minus 1 by twice by j. You have integration of gamma r. Might have semicircle xp 1 minus e to the minus ts minus p. So integration over around that infinite semicircle, again, two cases is being considered here. The case one is strictly proper transfer function. Okay. And in the particular case, they are interested about the initial value. So they are actually using that formula of limit s tends to 0. Limit s tends to infinity s x of s equal to x 0. So initial value. So if your numerator is 2 or more pole, and then the zeros of this equation access, in that case this vanishes and becomes 0. And if it is not true, that means your equation is excess is proper, not strictly proper, or in this particular case one pole is the number of the pole is higher by 1, and then the zeros. In that case, we can have this one is not getting 0, rather it is becoming a constant. Okay, so somehow it is minus half of x0 plus. But as we said that we are not going to use this method for solving the actual real life problem. So this derivation is not done in the book, and also I haven't seen the use of this equation, this constant. So it's just remaining as a constant. So whatever the value, if you see that your Q of S is having one less zeros compared to the pole, then you just have to exclude that parameter. That's it. So mathematically or for solving problem, they're not that important. Okay, so okay, so let's go for the actual method. So the case one, in the case one, case one inside case two, that is this one. Okay, so in this case, this one is vanishing to 0. In this case, it is becoming minus. Addition, already you have a minus, so minus minus will be plus, minus half of x0 plus. So we can take it that way. We are not going to go into the derivation how this is becoming half of the initial value. So, but we are interested about the first portion, which is this one. This will be easier, will be utilized to understand the sampling theorem later part of this chapter. So we finally say that x star s is basically 1 by twice by j with a negative sign as well. Integration clockwise xp 1 minus e to the power minus ts minus p dp. So we're going to use the same residue formula. So the formula is the same. We will have to bother. But the question is the poles. So now, as you can see, which poles we have to consider. The point is that now the poles of 1 minus 1 by 1 minus e to the power minus ts minus p is now actually enclosed. So we have to actually find out the residue of those particular poles. So actually, what are those poles? We have to calculate that first. So based on this formula and based on the residue, we'll be calculating, no doubt about it. But what is the pole? So basically, the poles are the denominator. So basically, 1 by e to the power minus t is minus p equal to 0, you have to set. Now, if you set it this equal to 0, what we find is e to the power minus t s minus p should be equal to 1. And we know that e to the power twice pi is 1, and also any multiplication of that is 1. So basically k equal to 0, 1, 2, whatever it is. So this is the scenario. So based on that, minus t s minus p equal to twice pi k. So minus s plus p equal to twice pi by t k, and twice pi fs is the sampling frequency. So s p. So we can also write in terms of the frequency in terms of omega. Okay, so sometimes we have to encounter this problem with our tab. Okay, so we can also write it as omega s, okay, in terms of radians. So minus s plus p. So the poles of that one is basically p equal to s plus omega s. Okay. Okay, so one thing we missed actually, and that is we have to give a j here. Okay, because it comes with e to the power j theta equal to cos theta plus j sine theta. And for e to the power j twice pi, we basically cos twice pi, and sine is always 0. So that one is vanishing. So twice pi, and if it is k, then it will be carrying correspondingly. So basically, for each of them, you have j involved. And also, one thing is that it is also true for plus minus of k. So whether it is plus twice pi or minus twice pi, it will be also same. So we can also give plus minus everywhere here. So what we have here is finally plus minus j omega s k. So that is why you have infinite number of poles, as we see. This is amount s. So if it is p plane, and p is deferred by s, and s say equal to k equal to 0, then this one, k equal to omega this one, k equal to minus 1 this one, k equal to minus 2 this one, plus 2 this one, minus 2 this one. This is how is becoming infinite number of poles for your 1 by 1 minus e to the power t minus sp. Okay, so it's true now. So we know that the pole location. So because pole locations are important to find out the residue. So our residue theorem x star t, x star s equal to minus summation of k equal to now minus infinity to plus infinity, because starting from minus infinity, it goes to plus infinity. So and then you have to have that limit p tends to s plus j omega s k. And then that function will be multiplied by the pole. So pole is at p minus s plus j omega s k. And then the same thing that what we have done previously. This is what we are repeating. Okay, so what we have done is the pole, the function is multiplied by the pole, the pole interest, like this one. Function is multiplied with that. What is the function? Function is xp, 1 minus e to the power minus t s minus p. Okay, so the function is multiplied. Then you put the limit. Then now you may ask why only positive sign, negative. Negative is actually taken care of here. Okay, so from minus infinity to plus infinity, so it is already there. Now the problem here is how to find out this one. Now we have to take the help of L'Hopital's rule. So this is actually, if you put the magnitude, this is a pole, so it will be giving a 0. and this one is a pole as well, so it will also give. So it is actually become 0 by 0. So now L, we know this formula is L Hopital. Actually, it is a French name, so it is not L Hospital or L Hopital, rather it is L'Hopital. So L'Hopital's rule is something like this. If you have 0 by 0, then you have to differentiate both the parameter with the corresponding value. So d by dp of the numerator, that is p minus s plus j omega s k, and also d by dp of the 1 minus e to the minus t s minus p. Okay, then you have to set the limit, that is e tends to s plus j omega sk. This is what is the L'Hopital's theorem. So let's try to do that on that one. Okay, yeah. So minus k equal to e minus infinity to infinity, then d by dp of p minus s plus j omega sk, then d by dp of 1 minus e to the power minus ts minus p, and then xp is also there. Then on the whole thing, you have to set p equal to s plus j omega sk. So it will be simply 1 in the numerator. So minus k equal to minus infinity to infinity xp by d by dp 1 minus e to the minus ts minus p. Let's do that limit separately. Then we'll replace the value here. Okay, obviously don't forget this is your x star s. Okay, so the limit in the denominator, so d by dp of 1 minus e to the power minus t s minus p, then you have to set p equal to s plus j omega sk. So if you do the differentiation, it will be minus e to the power minus ts minus p, exponential remains as it is. Then you have minus, then you have minus ts plus tp. So p with respect to p, so it will be basically become simply a t. And then you have to set equal to p equal to s plus j omega sk. So what will it become is now you have to set what you have minus t. It is where minus t s can be replaced. P can be replaced by s minus s plus j omega s. So s minus j omega sk. So basically s is getting cancelled out. Minus t to the minus t. J is also there, and omega sk. Omega is basically nothing but twice pi by t. Okay, so whatever left is minus t, then e to the power minus j twice pi k. So twice pi k is 1. This will give you plus or minus twice pi is always 1. So whatever left is minus t. So you can replace this value here, and then whatever we have is minus summation of k tends to minus infinity to k from minus infinity to infinity. Then xp, we haven't applied p values to the xp yet, so we just find out what is the denominator. Then e tends to s plus j omega sk. So now this minus minus will cancel out. What is left is k equal to minus infinity to infinity. Simply, we can put the value of p here. So 1 by t, which you can also take in the font. So 1 by t, then x s plus j omega s squared formula. So we can see that our x star s is becoming 1 by t, summation of k equal to minus infinity to infinity. Then your x is simply replaced by s plus x is, and the p is simply replaced by s plus j omega s k. Okay. Now we are interested about the z transformation. So s has to be replaced by 1 by t log z. So in that case, we can call it xz equal to 1 by t, summation of k equal to minus infinity to infinity. It's s plus j omega s k. Condition is s equal to 1 by t log z. Okay, as I already said, there is two conditions. In both conditions, this is true. Then in one condition, you have 0 added, and the other condition, you have half of the x0 is also, x0 plus is also included. So as I said, we're not going to use this one for mathematical problems. So we can just let it be as it is. Rather, you will be using this theorem for understanding some of the complicated theorem like sampling theorem in the later part of this chapter. So one example related to this one is there, example 3.2. I'll advise you. I will advise you to go through that one. So we'll not cover that. So the next thing that we can do is sometimes in some problems we see that 1 minus e to the power minus ts by s is actually multiplied with some factor. So somehow we can, if we can easily replace this thing with something. So eventually s is not replaced, rather 1 minus e to the power minus ts is replaced by 1 minus z inverse. So if we can replace this one, then we can see that the solution may become very, very easy. So just quickly look at that one. So say xs is a multiplication of 1 minus e to the power minus ts by s into g of s. So we can say that 1 minus e to the power minus ts, g of s can, s can go with the g of s. Then we say that 1 minus e to the minus ts into g1s. We just assume that this whole thing is g1s. Then you can just multiply. So you're going to have g1s minus e to the minus ts into g1s. Okay, so we call the later part as, just assume this one is the x1s. So so what you can see is that this is nothing but a delay, isn't it? So x1t, if you want to figure out what is x1t, is 0 to t is g0 t minus tau g1 tau d tau. Using the convolutional integral, this is what you can write. Okay, so we can say that g0t is simply the inverse Laplace transformation of e to the power minus ts. So which is, we know that it is just a delay with an impulse sample. So basically del t minus tau, and g1 t is nothing but Laplace transformation of g1s, inverse Laplace transformation of g1s. So we can replace this to value into this equation, and this equation will give us the time domain function x1t as 0 to t del t minus tau, the delay, G1. Then you have G1 tau, then d tau. So basically the magnitude of G1, whatever it is, it will be at this delay. So we can simply write G1 t minus t. Okay, so now what we know that we also know the Z transformation of GT time domain function is basically G1 Z. So and also Z transformation of XT, X1T, X1T, that whatever we have calculated will give us Z transformation of G1 T minus T, the delay amount. Okay, so equal to, and this is nothing but delay by one time delay. So Z inverse G1Z. So if we recall that XS is nothing but 1 by, it was our initially whatever we have assumed, x1 is e to the power minus e to the power minus ts into g1s, and we assume that this one to be x1s. We already find out what is x1s, z transformation of it. So whole z transformation of x, if you want to figure out, then we find that it will be z transformation of g1s minus e to the power minus ts g1s. Okay, so you can easily find out the inverse z transformation to find out g1t, and then you can this one will be what you have called is previously x1t, and using the convolutional integral we find out what is what the function is all about, and then we find out it is actually nothing but z inverse g1z. So we can write simply find out the z transformation of both of them. So this is what it becomes. So now you can just take comma of 1 minus z inverse g1z. So what was initially 1 minus e to the power minus ts g1s. So we can see that easily we can just replace this parameter by this parameter. Then we have to find out the rest of the z transformation of the rest of the parameter. Okay. So whatever we can see is that finally we can write that xz, if you want to figure out, and which is a z transformation of xs. If the function is given the Laplace transformation, then we can simply write this as z1 minus z inverse, which is just the replacement of 1 minus e to the power minus ts. Okay, so that one has been replaced, and then z transformation of g1. So in g1 inside g1s, as you know, it was g was initially by s. So whatever, if you have 1 minus e to the power ts, you simply replaces that one, and the rest of the portion you just take as z transformation. So this is how we can make things a bit simplified. So say we have a transfer function. We have a system, small system with first order hold, that followed by a transfer function gs. So we know that first order hold transfer function is gh1, which is equal to 1 by e to the power minus ts by s whole square. In the last class we have derived that one, ts plus 1 by t. Okay, so if you want to find out what is xs, which is just multiplication of gh1 into gs, then what we have to do is we can simply write the transfer function of the first order hold, okay, in square terms, then ts plus 1 by t, then you have gs. So 1 minus e to the power minus ts, remove the s square from the denominator and include it here. Okay, then g of s. So If you want to find out the Z transformation of this one, then XZ will be simply Z transformation of the whole thing, this one, and eventually we know that 1 minus e to the ts can be replaced by 1 minus z square. So we can write 1 minus z inverse whole square. Then you have to find out the z inverse, z transformation of ts plus 1 by ts square into gs. So this is how the solution somehow been simplified by simply replacing 1 minus e to the ts by 1 minus z inverse. Okay, so one example related to this one is example 3.3. Example 3.3. So xs is given 1 minus e to the power minus ts by s. Then you have 1 by s plus 1. So what you can do is we have to find out the z transformation. So z transformation 1 minus e to the power ts by s, 1 by s plus 1. So you just isolate that portion and replace it by 1 minus z inverse. Then the rest of the thing, you find out the z transformation, s is plus 1. So use the partial fraction expansion before applying the z transformation. Okay. 1 by s minus 1 by s. We have done that before, so I'm just writing it quickly. So it will give you 1 minus z inverse. Now, since we know the time domain function of this one, 1 by s is simply nothing but 1 t. Okay, step signal 1 t, and this is nothing but e to the power minus t. And from the table 2.1, we know there's a transformation of both of them. Okay, so there's a transformation of the first one is 1 minus 1 by 1 minus z inverse, and z transformation of this one is 1 by 1 minus e to the power capital T z inverse. So we'll just solve a bit, and then we'll find 1 minus e to the minus t z inverse, 1 minus e to the minus t z inverse. Okay, so this is your solution. So simplified a bit by replacing 1 minus e to the power minus ts by 1 minus z inverse. Okay, let's let the class end here today. So I can move on.